We continue our discussion about the generalization risk of learning. We start from the Hofstad's inequality for a single hypothesis, and we see that does not directly apply to a hypothesis family that contains infinitely many hypotheses. Then we established the relationship of comparing the in-sample error and out-sample error, and that means the difference between comparing two independent in-sample errors. And then we established that it's not the number of the hypotheses in the family that matters. It is the number of possible dichotomies a hypothesis family could possibly generate on a finite set of training examples that matters. And we reached the point that if we consider the intuitive limit, that is, a hypothesis family could generate all possible combinations of positive negative classifications. That means all dichotomies on the 2n data set, which is of no use for establishing a limit of the generalization error. And in the following discussion, we will consider the capacity, that means the maximum number of dichotomies that could be generated among all the members in the hypothesis family on some limited number of data points. Here should be points or samples. Of course, as long as the number is limited, it does not matter if we consider the capacity on 2 endpoints or endpoints. So we keep user n here for concise samples. We define a quantity with respect to a hypothesis family and the number of examples, data samples. So that is the we first assume that we have the functionality that helps us to count all possible dichotomies that can be generated by a hypothesis family on n data samples. And then we consider among all possible arrangement, all possible outcomes of drawing n random samples from the data space. So for each of the instance of such n samples, we count the dichotomies generated by this family, and we consider the maximum possible number of dichotomies by arranging the n data points and counting the dichotomies generated by the family of interest. So let's have a look at an example of counting the dichotomies generated by a family. Say the family is a linear family. Let's consider a linear classification model on 3 data points of 2 dimensions. So the 3 data points could be in this way, arranged in this way. So we have a hypothesis. Such a linear hypothesis could be represented by a straight line on the 2-dimensional plane. Let us see, on this side, the hypothesis will predict it as a positive, see the green class, and on the other side, the classification is red class, negative. So for this hypothesis, we can generate this result for the 3 points, and then we can flip the prediction of the hypothesis, which is totally doable for a linear model. See, on this side, we consider it to be negative, which is represented by red, negative class, and on that side, the classification is positive and green. So by simply flipping the result of the four cases on the top row, we get the four cases on the bottom row. So we totally have 8 distinct different classification results on the 3 data points, and therefore we have exhaustively generate all possible dichotomies on these 3 points. So the number of the dichotomies on these 3 data points is 8, and 8 is also the maximum possible number of dichotomies generated on 3 data points, because 2 to the power of 3 equals 8. So we can say that the capacity of a linear dichotomy, a linear hypothesis, reaches is sufficient to generate whatever kind of classification result on 3 points. Please notice in the definition of this function represents the capacity of each on the n data points contains a maximization. That is to eliminate some special and singular arrangement of the data points that you do not. You want to calculate the capacity of the hypothesis family on generic settings, where we want to exclude some very special arrangement that does not represent the general cases when we draw random samples. Say, for example, for 3 data points and a linear model, there are some arrangement of the points that does not allow the hypothesis family to generate all possible combination of the samples. Say, if the 3 data points are on the same line, so there are maximally 6 different cases could be generated. If you can imagine, if you have 2 points on either end have the same color, and the sample in the middle has a different color or class, then this case will not be generated by any linear hypothesis. However, this is a very special spatial arrangement of the data samples. We don't want to consider these cases. Okay. So we consider the maximum number of dichotomies that could be generated by freely arrange the data points so that it facilitates to generate a large number of dichotomies using H, capital H. And in the next, there is a very important concept called breakpoint. So we have seen that the linear hypothesis family can sufficiently classify the binary classification on 3 points by generating all possible dichotomies of 2 to the power of 3 equals 8 cases on the 3 points. And you can imagine that if a hypothesis family want to keep up this capacity when n grows, when n is larger, the task can become more challenging. So when there is a point at which, for example, some k, at which the family of hypotheses, the capital H, cannot no longer generate the complete combination of the 2 to the power of n hypotheses, no matter how you try to arrange spatially the n points, then at this point we say k breaks the hypothesis family when the maximum number of hypotheses on n points stops being equal to 2 to the power of n. So a concrete example in the previously discussed linear hypothesis family is just 4 points. We can see that for 4 different generically arranged points on 2-dimensional space, there could be 2 to the power of 4 equals 16 possible combinations of the dichotomies. But these 2 cases cannot be generated by any kind of linear hypothesis, linear classifier. So n or k equals 4 breaks the linear family of classifiers. That is the linear classifier family's breakpoint. Very important implication of a breakpoint is that now when the number of data points grew, then once broken, always broken. So say if for some k breaks the capital H, the hypothesis family, then for any n which is greater than k, n must break the hypothesis H. H could not possibly generate the complete combination of 2 to the power of n dichotomies on the n hypothesis on the n data points when n is greater than k. Otherwise, we can take a subset of the n points of k points, and because of the fact that the hypothesis can generate the complete set of the combination of 2 to the power of n dichotomies on the n points, it must be able to generate 2 to the power of k dichotomies on the k subset, which contradicts with our previous assumption that n breaks H. So once broken, it's always broken. And we have the conclusion that when the number of maximum possible hypotheses, dichotomies, and some k or n data points, when it's broken, it's always broken into polynomials in terms of the number of data points. So to be specific, the number of hypotheses generated by the family on n points when n is greater than the breakpoint k is at maximum is uplimited by this sum. This sum is polynomial with respect to n. Well, this sample represent, we take I element, the number of possible choices of I element without replacement out of n. So if n equals 3, I equals 1, this is 3. There are 3 possible ways to take 1 element from 3. If n equals 5 and I equals 2, then this number equals 10, because there are 10 ways to take 2 different elements from 5. So this anyway, this is a polynomial function with respect to n. Okay, if we substitute this equation into the number of possibly generated dichotomies in our upper limit of the generalization risk, I think, excuse me, this should be 2n. That means we want to limit the generalization risk by multiplying the risk of individual hypothesis with individual case, a scenario where two independently evaluated in-sample error differs by some amount exceeding the threshold, times a factor that is limited by this number, the MH, the maximum possible dichotomy number on 2n data samples. So, and this is polynomial, and this is minus exponential to the power of the minus term in terms of n. We have this trend as we have seen previously. So we putting everything together, we have the possibility of the upper limit of the in-sample error and out-of-sample error within a hypothesis family is greater than some threshold epsilon. It's bounded by twice of the possibility of the in-sample error, the difference between two independently evaluated in-sample errors is greater than half of epsilon. And that is limited by 2 times this factor, which if you do the math correctly, you arrive this 4 times mh2n, which then multiply by this exponential term. This conclusion belongs to Vapnik and Chervonenkis in 1971. And the breakpoint, I think that the value, if the breakpoint of a hypothesis family is finite, is not infinity, which means there exists some number of data points which is the maximum possible, which is at this number, the maximum possible generated dichotomies by h is smaller than 2 to the power of the number. So this is a breakpoint where the maximum possible number below the breakpoint is called a VC dimension of a hypothesis family H. Anyway, when the VC dimension is less than infinity, then we would see this term is polynomial with respect to n, and eventually the generalization risk will be bounded asymptotically. That means when n goes to infinity. And the polynomial is given in this equation. In an extra video, we will briefly discuss how this is established. For a sketch, it's used the same kind of argument when we consider once broken, always broken. We consider the cases when the number is greater than the broken breakpoint, and consider in that case how the dichotomies could be categorized into different groups, and then we establish by using mathematical induction to establish that bound. So to summarize, we eventually have a useful generalization error for learning. So learning will work.